Welcome back to BE544. In lectures 5 and 6, we explored how polyslide images are structured, navigated, and decomposed into tiles for computational analysis. Today, we shift focus to the core modeling phase, how we classify histopathology patches or tiles using deep learning architectures. Patch-based classification is the most common strategy for analyzing gigapixel whole slide images. Rather than processing the entire slide at once, which is computationally feasible, we divide it into smaller, manageable patches or tiles. For example, 256 by 256 or 512 by 512 pixels. Each patch or tile is then classified independently, and predictions are aggregated to form a slide-level diagnosis. There are multiple architectural paradigms that can be used in classification, such as Convolutional Neural Network, or CNNs, which can be designed from scratch or fine-tuned from pre-trained models such as ResNet and VGG. Vision transformers, which treat image patches or tiles as sequential tokens and apply self-attention mechanisms, YOLO, or you only look once. And this technique was originally developed for localization, but later enhanced to apply classification, hybrid designs, which can combine CNN feature extractors with transformer encoders to utilize both local and global context. And we are going to cover all of those in this course. The choice among them depends on data size, computational resources, and the diagnostic question. In this lecture, we will start by understanding the convolutional neural network and the terminologies behind it. A CNN or convolutional neural network is a specialized deep learning architecture designed explicitly for grid structured data like images and can be applied also for videos. Unlike traditional neural networks that rely on matrix multiplications, CNNs use convolution operations, which are sliding small filters across the input to automatically detect the spatial hierarchies of features. So each layer in CNN capture low-level patterns like edges and textures, and deeper layers assemble these into complex structures like nuclei, glands, or stromal invasion faults. Again, CNN use the convolution operations, which differs from matrix multiplication in traditional neural networks, with the help of something called filters. And by applying the filters on the input data, like images or the tile in our case, we can adjust these built filters during training that will facilitate the real-time fine-tuning of results. So it's like building a matrix, and we are tuning that matrix so that it can understand the input. And by automatic tuning and updating these filters, we are now eliminating the necessity of manually handcrafting the features that reflects the input. So the story is simple. There are two approaches that we covered earlier, which are called machine learning and deep learning. And simply CNN, which we are discussing now, is a type of the networks in deep learning. And to make it simple, in machine learning, you need to extract features, whether using an equation or an algorithm, but in all ways, you need handcrafted features from the input data. Let's say we are gathering the area of the nuclei, the number of nuclei in a specific tile. These are all features, and we will later inject them into a machine learning model like KNN or support vector machine. But the story here is different. In CNNs or deep learning, the adjusted filters eliminate that by teaching those filters on the input so that it can extract the features automatically. After getting the idea of using CNNs and the beneficial point of automatic feature extraction, which is applied internally in the CNN, we need to understand the type of layers that build that CNN. A CNN will start by an input layer, and this input layer will receive the raw data, which are the tiles in our case. And each tile is a multidimensional array or a matrix. Let's say we are dealing with color tiles and we need to apply classification on them, then the input layer will accept those colored tiles as matrices. Each tile or image is represented by width and height and color channels. So if you are dealing with a tile with 512 by 512 as dimension, then this image, which is colored, will be stored as a matrix of height by width by 3. And the 3 here reflects the RGB, which we say colored image, where R is red, G is green, P and blue. So any image or any colored image will be stored like that. So the result will be 512 by 512 by 3. So assume that we have 10 images, so each image will be stored like that. Then we can apply convolutional layer. And any convolutional layer can apply the convolution operations as mentioned by sliding the small filters, or we can call it kernels, across the input data. Again, these filters are learnable and trainable. And during the training process, this will be tuned to capture the patterns of the input data, which we call automatic feature extraction. So each filter will detect a specific pattern, and the size of the filter and the number of filters are designed and determined during the network design. And we can call them hyperparameters. What does it mean? Simply, there are two terms. One is called hyperparameter, another called parameter. A parameter, as we are going to see, is like a weight or a value that will change during the training process. And these are the values assigned to the filters. And we mentioned that during the training process, these filters are tuned. So what we are tuning inside these filters are called parameters or values. And a hyperparameter is the predefined configurations, like how many neurons in that layer, how many layers that we are going to build, how many filters that we are going to use. And these hyperparameters are not trainable. So again, during the training process, we are tuning the parameters, and before running the training process, during the design process, we are setting the hyperparameters. After building a convolution layer, we apply an activation function. And this activation function will introduce nonlinearity to the network. So assume that we have some images and we need the system to classify them. So the idea is to map each image into the corresponding output. For example, get the tile applied to the system to get the final decision, which can be tumor or benign or whatever. So by looking on that mapping, we will consider that the relation between the input and the output is nonlinear. And the linearity here means when the input changes, the output will change by a constant or a factor. And this formula or this consideration is not applicable in all datasets. There may be nonlinear relationship between the input and the output, and this is the common case in datasets. So to do that and introduce that nonlinearity into our network, we use activation function. So the output from the convolution layer will be applied to the activation function, and the output of the activation function will be considered as nonlinear output. There are multiple activation functions like relo or rectified linear unit, which replaces negative values with zeros. And there is also sigmoid, which squashes the output between 0 and 1. And by introducing the activation function into our model, we can understand the complex relationships between the different features. And which activation function to use, it depends on your design and the type of the input data, and whether you are applying this activation function into the hidden layers or the output layer. And we will understand that during designing our network. So simply, we have an input layer followed by a convolution layer, and there is an activation function which is applied to that convolution layer to convert the input into nonlinear, which will later capture more complex relationships between the features. And after an activation function, we apply a pooling layer. And a pooling layer is used to downsample the feature maps produced by the convolution layer and activation function, which will help to reduce the spatial dimensions while retaining the important information or features. So If you refer back to our example, we need to map from the input tile into a decision, which can be 0 or 1. 0 means normal, 1 can be a tumor. And we mentioned that the image can be 512 by 512 in size. And this means we need by somehow to reduce the size of the image from being 512 by 512 by 3 as an RGB image into a numeric or a scalar value. So to do that, we use pooling layer. It will reduce the spatial dimensions. So instead of 512 by 512, it can be 500 by 500 depending on the configuration. On the same way, and also it will retain the most important information. There are multiple types of pooling layers like max pooling, which will select the maximum value within a certain window. There is an average pooling that will take the average value of a certain window. And there are also a beneficial point behind pooling layer, which is preventing overfitting and reducing the computational complexity. So assume that we are dealing with the same dimensions in each layer, 512 by 512, then the complexity of the overall system or network will be higher compared to downsampling or minimizing the dimensions during the layers. So the idea is simple. We need a layer or a component that can do multiple things. Reduce the spatial dimensions, so later we can get a final decision, which can be a scalar or a vector. Also, prevent any overfitting. And lastly, reduce the complexity. And overfitting here means that the model is learning on the training data, but when we test that model, it doesn't do well. And this is called overfitting. So the aim, we need a fitted model. Applying pooling layer, we can then use flattening. And the flattening converts from multi-dimensions into one-dimension vector. And that flattening and the conversion into a one-dimension vector will help to reduce that one-dimension vector into a scalar value. So imagine that the story begins by getting an input layer, which is 512 by 512 by 3. Then we used convolutional layer to capture the features, applying an activation function that will convert the output into nonlinear so that we can understand the nonlinearity relationship between the features. And then we need to reduce the size and dimensions alongside other mentioned benefits so we can use pooling layer. By doing that multiple times, we can reach to a reasonable and small matrix. After that, to be able to get a scalar value from that matrix, we need to apply flattening. So it will flatten that multidimensional matrix into a single vector or one-dimensional vector. And after that, we can use what's called fully connected layers, which consists of neurons arranged in a one-dimensional vector as well. And this fully connected layer will perform transformation on the flattened feature vector to map it to the desired output scalar value or space. And another benefit of the fully connected layer is to capture the high-level abstractions and relationships between the different features learned in the earlier layers. And after applying these fully connected layers, we can use an output layer, which is our output that can be tumor or not. So designing such a network will perform two things: automatic feature extraction and also classification by using those types of layers: conv layer, activation function, pooling layer, flattening, fully connected layer, and then an output layer with our prediction. To be able to update the network and tune it, aiming to get a higher performance in the prediction, we need a value to measure the difference between the predicted outputs and actual labels or ground truth labels. So we can use a loss function. And the aim during the training process is to minimize this loss function by adjusting the network's parameters. And as mentioned, the parameters are tuned during the training process. And this includes the weight and bias of each kernel or each filter. There are multiple loss functions like cross-entropy loss, mean squared loss, and mini-more. And each has a specific usage. and depending on the input type and application, we determine which loss function to use. Again, we need to tune and adjust the network parameters, which are weights and bias, during the training process using the loss function. So after each epoch or each try, we get a loss value. This loss value need to be reduced. How? By updating the weights or the parameters. By adjusting those weights multiple times, the loss function theoretically will be reduced. This process is called parameters optimization. So we use an algorithm that should perform that thing, adjust the weights and biases during the training process and minimize the loss function. These optimization algorithms has something called learning rate, and the learning rate controls the size of parameter updates, and it's a critical hyperparameter which is predefined before starting the training that will affect the optimization process. If we got or applied a very high learning rate, we may miss the minimum point or minimum loss value. And if you applied a very small learning rate, it will take much more time to reach the optimal point. So depending on the application, we try to find the most reasonable learning rate. Examples of the optimization algorithms like gradient descent or stochastic gradient descent, ATOM, or root mean square prop. Again, the choice of the optimization algorithm depending on the application and the dataset. And we can also try multiple optimization algorithms aiming to find the most suitable for our dataset. So simply, during the training process, we iteratively process different batches of input data, and these batches or images or tiles in our case will be propagated in a forward direction, aiming to get the predictions at the output layer. The predictions at the output layer will be compared to the ground truth or the actual labels, and using a loss function will compute a loss value based on the ground truth and predictions. This loss value will be injected by somehow into the parameter optimization algorithm, let's say stochastic gradient descent, and the algorithm will find the new weights and biases or the new parameters that will update the whole network, and this is called backward propagation or back propagation by computing the gradients of the loss function with respect to the network's parameters. By doing that multiple times, we can reach convergence where we may reach the ideal loss value, which is 0 or a very close value to 0 on the training data. So those multiple times of iterations are called epochs. So 50 epochs means we are applying forward and backward propagation 50 times. And after training the model and tuning it, we apply evaluation. And evaluation here determine whether the model generalizes well on unseen data or not. So imagine that we tuned a model for, let's say, 100 epochs, and we got a good performance. Then we applied it during the evaluation phase on unseen data and got a poor performance. This means the model didn't generalize well on unseen data while it performed well on seen data. In this case, again, we call it overfitting. But if the model performed well on unseen data, this is called a fitted model. To judge the model and its performance, we use performance metrics. And there are different performance metrics, and each has a specific use and importance, like accuracy, precision, recall, and we are going to deal with those performance metrics and understand how to calculate them. So the ideal point is to get a high performance model in the training and evaluation or testing. This means that the model is fitted, and let's say we couldn't get a generalizable model on the testing subset or unseen data, then we need to adjust our architecture or hyperparameters. So there is something called hyperparameter tuning. But let's stop for a second, as you may wonder, what's the difference between hyperparameter tuning and parameters tuning? If you remember from a while, we mentioned that there is something called parameter and hyperparameter. A parameter, which are weight or a bias, and these are values tuned during the training process, and these are the factors or the values of the filters that help those filters to capture the features, and you will find the parameter tuning during the training process. But hyperparameter tuning tries to find the most suitable configuration that can lead that model to get high performance. And again, hyperparameter mean a predefined configuration which is not injected into the training process or updated during the training process, like the number of epochs, number of hidden layers, number of filters per layer, the learning rate, the optimization algorithm, the loss function, and so on. And for simplicity, let's say we got different learning rates and we need to try all of them. So simply, we will pick the first one and train and tune the model based on that learning rate. After completion, we report the performance metrics. For the second one, we will repeat the same process from scratch. On the third learning rate, we will repeat it again from scratch. So for each trial and the hyperparameter tuning, we will train and evaluate the model from scratch and report later the performance metric. Now you understand the difference between parameter and a hyperparameter, and the difference between hyperparameter tuning and parameter tuning. And hyperparameter tuning is essential as we don't know what is the most beneficial and most important configuration that lead to the highest performance. The last thing is to store the model, because after tuning the hyperparameters and tuning the parameters and getting the required and reasonable performance, you need to store that model on your hard drive or hard disk because you need to use it later. What does it mean? Simply, the aim or the target of building a network and tuning it on the data is to apply it later into an application, because you don't have to apply training again and again on each prediction. You need to train and tune the model for just once, store that tuned model, and use it multiple times later. Also, the training time will be much higher than the prediction time. The testing time or prediction time in your application can take, for example, 10 seconds or 5 seconds, but the training process as a whole can take hours or even days. So it's not reasonable to train the model from scratch again when you apply just for a single tile in the prediction on your application. Now let's pick each layer and understand it well. The first layer is the input layer, followed by a convolution layer. And as mentioned, a convolution layer performs a convolution operation, which is a fundamental operation in image processing and computer vision tasks. Again, the goal of that layer is to extract features from the input data by using the learnable or trainable filters or kernels applied to the input. So a kernel or a filter is a small matrix filled by weights that slides across the input data, where each filter can capture a specific pattern or feature that represent the input. So for example, we can get and apply 3 filters. Each filter will detect and determine a specific pattern or feature, like detecting edges, textures, or shapes in the image. And the size of that filter or kernel is typically small, for example, 3 by 3 or 5 by 5. So imagine that we have a 3 by 3 or 5 by 5 matrix sliding over the 512 by 512 image. And the sliding here means moving from the left to the right and from the top to the bottom. And by applying that on the whole image, we get an output called output feature map. So the output feature map is the result of applying a convolution layer using a sliding filter or kernel on the input. Sometimes the output feature map may be smaller than the input. So in that case, we can apply what's called padding. And padding here is applied to the input data to ensure that the output feature map has the same spatial dimensions as the input. Padding can be zero padding by including zeros around the image, and there is called also valid padding, where no padding is added. And we mentioned for a second that the filter or the kernel slides over the input. The amount of that slide is called stride. So stride determines the step size at which the filter slides across the input data. So a stride of 1 means shift by a pixel, and a slide of 2 means shift each 2 pixels. So a convolutional layer can get a set of filters, a stride value, and a padding value. And those can be considered as hyperparameters and also can be tuned during the hyperparameter tuning and during also the design of our network. After the convolution operation, we apply the activation function, which again will introduce nonlinearity to the network. And this activation function is applied element-wise, and element-wise mean it will be applied on each element or pixel individually. The weights of the filters, as mentioned, will be tuned during the parameters optimization or through backpropagation of the optimization process, where its aim is to minimize the loss function and improve the performance of the overall network. To understand, let's get an example. Assume that you have a 5x5 image, which is here, and a 3x3 filter, which is here. This is a filter or a kernel. And let's say that we have a stride of 2x2, which means shift by 2 in width and shift by 2 in height. And assume also we have a zero padding or valid padding, which means that we will not apply padding on the input image. So simply take that filter, start from here until you reach the last pixel or according to the sliding window, and then calculate the output. How to do that? Get the first portion or the first window, which should be similar in size to the filter matrix dimensions. So if we have here 3x3, so we will pick 3x3 windows and then compute the convolutional output of it. How? Multiply each corresponding pairs and sum all of them to get the output. So 1 will be multiplied by 1, 2 will be multiplied by 0, 3 will be multiplied by 1, 3 multiplied by 0, 1 multiplied by 1, doing that until reaching 2 multiplied by 1. Summing all of those, you will get a value of 7. So this small window will be converted as a value of 7 in the output feature map. Doing that on the second window, we'll get a value of 8. And the second window in our case will be a window shift from the previous window by a value of 2 because the stride here is 2x2. How to determine that? Simply, we started from here. A shift by 2 means shift by 1, shift by 2, so start from here. Now we obtain the window, calculate the output, which is 8, fill it into the output feature map. There is no more shift to the right, then we will shift downward by a value also of 2 because the stride was 2. We will start again from the left, so we'll start from here because 1 with a shift of 1, with a shift of 2, because a stride of 2, we will start from 0. This would be our window. Calculate the output will be 8. Do the same for the last window. Calculate the output will be 7. Now, we converted or we extracted features from a 5x5 matrix into a 2x2 output feature map. This reduction resulted because we didn't apply padding. And if you remember from oil, we mentioned we can apply zero padding or padding with 0 values around the matrix, aiming to get the same shape of the output feature map to the input of the conv layer. To do that, you can simply add a layer filled with zeros that surrounds the original matrix. So instead of starting from here, we're getting that window, we start from here by getting that window. So how I know and determine the output shape of the feature map? Given that I know the input dimensions and the hyperparameters of our conv layer, you can simply use these two functions. The output width and the output height is similar but different values. To calculate the output width and height of the output feature map, simply apply flooring to that factor and add 1. The numerator will be the input width minus the kernel width plus 2 multiplied by the padding divided by the stride. So if we have a 15x20 image and a 3x3 filter matrix or kernel, a padding of 1, a stride of 2x2, we can simply substitute in these two formulas, getting the output dimensions of the output feature map. So For the width, it will be 15 minus 3, which is here, plus 2 multiplied by 1, which is the padding, divided by 2. This will be 15 minus 3 is 12, plus 2 will be 14, divided by 2 is 7. Apply flooring in case you have decimal points, plus 1 will be 8. So the new width will be 8. What about the height? 20 minus 3 is 17, plus 2 is 19, divided by 2 will be 9.5. Floor rate will be 9, plus 1 will be 10. If you remember, we multiplied each window by each kernel and sum all of that. And we can say this relation can be represented as a linear relationship. So to introduce the nonlinearity into the network, aiming to capture complex relationships and learn from nonlinear data, simply we introduce the activation function. And as you see on this figure, there are multiple activation functions, like the sigmoid, which squashes the input to be between 0 and 1, and relo, which ignores negative values and start a linear relationship between the positive values. There is also tanh by applying this equation on each value in the input, and there are many more. Now let's move to the pooling layer. Again, as mentioned, the aim of pooling layer is to downsample the output feature map, aiming to keep the most important features and reduce the spatial dimensions of these output feature maps. Therefore, these layers can reduce the computational complexity and overfitting. There are multiple types of pooling layers or operations. Max pooling, where we select the maximum value within a specific window, let's say 2 by 2 window. So we will pick the maximum number of that window. Average pooling, where we compute the average value. Global pooling, where we aggregate the information across the entire feature map to produce a single value for each feature map, and is commonly used in final layers of CNNs during the classification process. The pooling layer has also a sliding window and a stride value, but it doesn't have number of filters. So again, the sliding window slides over the entire output feature map with a specific stride, which is a step size, and pick the maximum value if you are using max pooling, or the average value if you are using average pooling, or convert the whole output feature map into a single value if we are using global average pooling. So the benefits of the pooling layers, as mentioned, dimensionality reduction. There is also two other important features and benefits, which are cancellation invariance, where the pooling helps make the network more robust to small variations in the position of features within the input data, and therefore it can help to generalize to unseen data. Feature localization, where the pooling layer retains important features while ignoring any irrelevant details, and that will make the network focus only on the most discriminative information for the task in hand, like distinguish between tumor and non-tumor tiles. To understand how the pooling layer works, let's get this example. Let's assume that we have a 12 by 12 feature map and a 5 by 5 max pooling layer with a stride of 2 by 2 in both directions. So simply what we will do now is to get a window of 5 by 5 like that, and because we are using max pooling, we will pick the maximum number in that window, which is 6, which is here. So this 5 by 5 window will be converted into a scalar single value, which is 6. Now move to the right by a stride of 2, we will obtain that window with a maximum value of 9. Do the same until you complete the whole image or the whole output feature map to get the output from the pooling layer. We can also determine the dimensions of the output from the pooling layer using these two formulas. They are similar to the previous two formulas, but here we don't have the width and the height of the kernel. So assume that we have 25 by 20 feature map and a 3 by 3 max pooling with a stride of 2 by 2. So the output will be 25 minus 3 over 2, floor that value plus 1 will be 12, and the same for height will be 9. So 25 by 20 will be converted after applying pooling into 12 by 9. Again, we apply conv, activation, and pooling aiming to extract the most important features into the network. Then, after the automatic feature extraction, we need to apply the classification. So from the flattening until we reach the output, we now apply classification on the extracted features from the previous layers. And because fully connected layers require the input to be in one dimensions, we need also to apply flattening. So apply flattening. This will convert any multi-dimensions into a single vector. And from that point until you reach the output, you can apply multiple fully connected layers depending on your design to capture the abstractions of the features. To obtain the number of elements in the flattening layer, we simply multiply width by height by depth because we convert all of the elements into just a single vector. We don't do any processing. So assume that we have an output feature map or an output from a Boolean layer by the shape 8 by 8 by 64. This means that we have around 4,000 elements in the flattening layer. The fully connected layers can be also called dense layers, and they are used to map the extracted features to the desired output space. Also, they learn complex patterns and abstractions, and also relationships from the input data, which is the output from the flattening layer. These fully connected layers contains neurons, and each neuron in a specific layer performs a weighted sum of the inputs from the previous layer, followed also by an activation function. Again, this activation function will introduce nonlinearity to capture the nonlinear relationships between the features and to make predictions. So we have two types of activation functions. Activations related to the conv layers and another activation which is related to the fully connected layer. After applying multiple fully connected layers, we reach the output, and the number of neurons in the output depends on the number of categories. So assume that we have three classes, grade A, grade B, and grade C for a specific tumor. Then the number of neurons in the output layer will be 3. And in this case, we call it a multi-class classification because we have multiple classes more than 2. And if we have a binary classification, which we distinguish between two classes only, we set a single neuron in the output, where if the output of that neuron is above a specific threshold, it will be reflected as 1, and otherwise it will be 0. So imagine the design. We have an input layer followed by the feature extraction process, which is done automatically to extract features from the tiles or the input, followed by the classification, and at last we need the output, tumor and non-tumor. So in the feature extraction process, we use convolution layer followed by activation functions followed by pooling layers. We can apply multiple blocks of conv bool layers like here. There's first conv and first pool. There's a second conv and second pool. And by increasing the depth or the number of those blocks will increase the possibility of capturing precise features. And the number of those blocks also depending on the input data, because sometimes you can increase the number of those blocks and get poor performance. While if you applied a simple design using just 2 blocks or 1 block of conv pool layer, you can get better performance. So this depends on the data, the project, the application. You design the corresponding model. Try it multiple times, aiming to reach the most suitable design with the most suitable hyperparameters for our data. Then here you will apply the flattening, which converts those outputs into a single dimension or single vector, followed by multiple fully connected layers, and lastly the output layer. Now we need to start to design this network, where our aim is to build 3 blocks where each has conv, activation, and pooling layer. And these 3 blocks are followed by a flatten block, followed by 2 fully connected or dense layers and an output layer. So go to script number 9, simple CNN design, where first we imported the TensorFlow and the Keras package, and you need to install it before usage. So simply go to TensorFlow website and then navigate the installation manual and start installing it. And TensorFlow simply is a package that can help you design different models, tune them, and report the metrics, curves, and so on, simply and in just a few lines. And also, it can help you to build different deep learning models, including CNNs, which our focus now. So here, what we did is to import the different layers from Keras, from TensorFlow, import the different optimizer, loss functions, metrics, and models. So star here means import everything from this class or this file. First, we determined and defined the input shape, which here is 128 by 128 by 3, height, width, and the channels. And the 3 reflects that we are using RGB or colored images. Then we designed our model using the sequential class, and this sequential class simply accepts a list, and this list contains the layers where we insert it one by one from the input layer to the output layer. And as you see, we started by the first block where it contains conv layer or convolutional layer, an activation function, and a pooling layer. And the parameters here are, the parameter in the first place here is the number of filters. So as you see, we started from 32, doubled it into 64, doubled it into 128. We set that the kernel size of each filter is 3 by 3 with a stride of 2 by 2. We set the padding is same and the input shape, which is defined here. And we define the input shape only in the first block because this one will get its input from the input layer or from the layer with this input shape. Then we use the pool size of 2 by 2 in the max pooling layer, and here we will reduce the size by 2. Now, as you see, we have the first block, the second block, the third block, and all of them share the same configurations, unless only we changed the number of filters. We doubled it block by block, and this depends on your design. You can change it depending on your application. And by increasing the number of filters, you are increasing the complexity of your model and the number of parameters. Then we use the flattening to convert from multiple dimension into a single dimension or one vector, applied to fully connected or dense layers with number of neurons in the first by 128 and the second is 64. Both of them has the same activation function, which is relo. This is the output layer. Here we use 3 classes, and the output layer has also an activation function. You can use the softmax if you are using multi-class classification, and you can use sigmoid if you are using binary classification. And in the case of using or applying binary classification, you will change the number of neurons to be 1, and the softmax will be sigmoid. You can use the summary function to print a summary of the model architecture. As you see here, there is the output of the summary function. It shows the architecture alongside the output shape of each level and the number of trainable parameters and the total number of parameters, including trainable one and non-trainable ones. Then you need to compile the model, preparing it for the tuning. And inside it, you define the optimizer, which will start to calculate the loss function, update the weights and the biases, and so on during the training process. And here we used the Adam optimizer. There are multiple optimizers that we are going to use, including Adam and stochastic gradient descent. The loss function, which is a function that will calculate a value using the ground truth labels or actual labels and the predictions. And here we are using categorical cross entropy. And in a future lecture, we will understand the difference between different loss functions, including categorical cross entropy and sparse categorical cross entropy. Here, we can apply also the metrics to track the performance. We can use different metrics, also illustrate what is the meaning and benefit behind each of them. But for simplicity, let's say we are tracking the accuracy of the system or the model. And the accuracy here means the number of correct predictions. So simply, you import the libraries, design your model, depending on your data, application, and whether you need complex architecture or not. You can print a summary. You will need to compile the model first before starting the training. Now we need to understand how to calculate the number of trainable parameters per layer. So simply, if you are in a convolutional layer, then you will need to multiply the kernel height by the kernel width by the number of input channels plus 1 plus the number of output channels. So the kernel is 3 by 3 and the number of channels are 3 plus 1, and the channels of the output means the channels or the number of channels in the current layer. And for a conv layer, the number of output channels is the same number of the number of filters, which are 32. So how to determine the number of parameters for a certain layer? Simply, for a convolutional layer, multiply the kernel width by the height by the number of input channels from the previous layer plus 1, multiply all of that by the number of output channels, which is the number of filters in the current convolutional layer. So for the first conv layer, which is here, we multiply 3 by 3 by 3 because the kernel is 3 by 3 and the number of input channels is 3, plus 1 multiplied by 32 is 896, which is here. And for the second conv layer, which is here, 3 by 3 by 32, and 32 is the number of input channels from the previous layer, which is here, multiplied plus 1 multiplied by 64, which is the number of filters in the second conv layer. This will be the total number of parameters, which is here. And for the dense layer, you add 1 to dn, and dn reflects the number of neurons in the input layer multiplied by the number of neurons in the output layer. So here we add 512 by 1, so it's 513 multiplied by 128, with this will be the result. And for the last dense layer, which is here, 64 plus 1 is 65 multiplied by 3, which is 195. So now you can calculate the number of parameters for a conv and dense layer. What about other layers, like max pooling and flattening? Both of them doesn't have kernels or neurons to be trained, or weights or biases. So the number of trainable parameters in max pooling and flattened layers are zeros. That's why the model got a result here by 0, 0, 0 for max pooling and 0 for flatten. So what we covered in this lecture is the convolutional neural network, which is a type of the deep learning models. And the CNNs are suitable for capturing features and applying classification on images and videos. In our case, we need to apply them on our tiles, which are extracted from the whole slide images. We went through the different blocks that build the CNN, like conv layer, activation function, max pooling, dense layer, flattening, input layer, and output layer. We knew how to calculate the dimensions of the output from the max pooling and conv layer. We also know the difference between the multi-class classification and the binary classification. Then we went through how to build that using Python and how to determine the number of parameters of a certain layer. And we mentioned that the max pooling and the flattening layer do not have trainable parameters. That's why the number of parameters from the model summary are zeros. Now you can start designing your own model by changing the number of blocks, whether increasing or decreasing, changing the number of dense layers or fully connected layers, running the script, and checking whether you can calculate the number of total parameters or the number of parameters per layer.